Okay, you might remember these were the two problems that we did initially with the area of the triangle. I'm going to show you how to do this problem using the actual definite integral definition. So we've got the definite integral from 0 to 2 of 2x dx. My first step is to find the antiderivative of 2x, dropping off the constant of integration c. So the antiderivative of 2x is x squared. And then normally we would put plus c, but because this is a definite integral, we're going to put a little line. I'm going to put hooks on it for this first time, but very often we drop those hooks and we just put a vertical line. So x squared evaluated from 0 to 2. Now remember that 0 is the lower limit of integration and 2 is the upper limit of integration. So when we're evaluating this, we have f of 2 minus f of 0. F of 2 is 2 squared. So we're going to put a 2 in for x. We get 2 squared. And f of 0, we're going to put a 0 in for x, and we get 0 squared. 2 squared minus 0 squared is 4. And that was the answer to our first problem. Okay, if you want to give this a try, you can give this a try. Okay, now on this, when you look at my work, you can see that I did not, I'm looking right here, I did not put the little hooks on that vertical line for the lower and upper limits of integration. It's really a personal preference as to which one you use, whether you use the one with the little hooks on it or just a vertical bar. Many mathematicians will use just a vertical bar. Okay, so let's now go to example 2. So now that you know an application of the fundamental theorem of calculus, which describes a way of evaluating our definite integral, we can go into example number 2, where it asks us to find the area of the region bounded by the x-axis and the graph of f of x equals x squared minus 1, evaluated from x equals 1 to x equals 2. So it is very helpful to understand what these curves look like. So f of x equals x squared minus 1. When we put a 0 in, we get negative 1 out for f of x. When we put a 1 in, we get a 0 out. When we put a 2 in, we're going to get a 3 out. So we know that this is a parabola that's going to look like that. And the part of the curve that we're looking at is from x equals 1 to x equals 2. So we're looking at this section right here. Let me make this straight because this is a straight line. There we go. And this is a straight line. But this curve is not straight. This is a curve. So we can't use the area of a triangle because it's not a triangle. Because if we look at that as the hypotenuse, that blue hypotenuse is not a straight line. Therefore, we have to use calculus. So we're going to write our integral evaluated from our lower limit is 1. So that lower limit is 1. The upper limit is 2. So your limits of integration are your values along the x-axis where your area is going to start and where it's going to end. And then the curve, which is that blue part right there, is going to be x squared minus 1 And then we have our differential dx. So we're going to evaluate this. This is going to equal the antiderivative of x squared is x cubed over 3. The antiderivative of negative 1 dx is going to be negative x, and we're going to evaluate that from 1 to 2, from x equals 1 to x equals 2. So in blue, we're going to have f of 2. So f of 2 is going to be 2 cubed over 3 minus 2. This right here is f of 2. And then we're going to subtract from that f of 1. And f of 1 is going to be 1 cubed over 3 minus 1. In place of x, we'll put a 1. And when we subtract those two values, we're going to get 8/3 minus 6/3. I'm going to move over to the right because I've run out of room, but I'll keep color coding. The blue subtraction is 2/3 minus the pink subtraction, 1/3 minus 3/3 is negative 2/3, and 2/3 plus 2/3 is 4/3. And let me move this over here so that you can see. Okay, here's one for you to try. Okay, we have the integral from 2 to 3 of x squared plus 1 dx. I'm going to draw a quick picture only because I can. This is a quadratic shifted up 1. So we're going to get this parabola right there. We're going to have from x equals 2 to 3. I better move this parabola down there. There we go. So from x equals 2 1, 2, 3, 4, 0, 1, 2, 5, and 3, 10. So I've got that curve from x equals 2 to x equals 3, and you can see that we're going to be finding the area of this shaded region. Here's our x-axis from 2 to 3. But using calculus, this is going to equal x cubed over 3 plus x evaluated from 2 to 3. So we're going to have 3 cubed, which is 27 over 3 plus 3, minus 2 cubed, which is 8 over 3 plus 2. 9 plus 3 is 12. 8/3 plus 6/3 is 14/3. So we have 36/3 minus 14/3, which is 22/3. This is where fractions are inevitable. Fractions are inevitable. Okay, in our next example, example number 3, we are going to do a little bit more evaluating using some substitution when we need to. So we're going to be pulling all of our tools that we've used thus far into finding definite